Hi then, and hello again. Morgan here. Page 13 of our outline. This is one of my favorite pages of the whole year. I got to admit that to you, because we're talking about the kinetic nature of matter. And this word comes from movement, okay, kinesiology. Now, the ice cream graph. Richard Erdman at Venice High School, who is a truly talented chemistry teacher, came up with this name to help us remember what this looks like. So I'm going to have to collect a few different colors here for today to do these graphs because they're a little complicated. There's a lot going on here. First off, my axes. I'm going to do my axes. Put them in green. Make it stand out. And I'm going to end up actually doing two of these today that are side by side. Okay. Now, what I'm going to be graphing is the number of particles versus speed. And there are different ways of labeling this. This is just the way I happen to like it. And convenient for when we're talking about gases. Now, some background. I actually can't tell you how fast a specific particle in a gas sample is going to move. But I know that if I have a large enough sample, the majority of the particles are going to behave the same way. I know what most of them are going to be doing. But I can't isolate one specific particle. Now, I also know that I'm going to have outliers. They're going to be behaving a little bit differently than the others. Okay? So let's imagine, first I'm going to draw a curve that looks like that in blue. Then I'm going to draw a curve in red. Now, the area under both of these curves represents the same number of particles. The reason I'm saying particles is they might be molecules, they might be atoms. Let's just be open-minded about that. Now, the blue line is a lower temperature, T1. The red line is a higher temperature, T2. That's my color coding. And T1 will be less than T2. So, at the lower temperature, the majority of the molecules will be moving slower. Now, there can be outliers that are going slower or faster than all the others. That can happen, okay? But the majority of them will be moving slower. Now, at the higher temperature, the majority of the particles will be moving faster. Now, more particles on average will be moving faster at a higher temperature than at a lower temperature. But could there still be an individual particle that is outlying more than the others? Much slower, much faster? Yes, that can happen. I can't say what one particle is going to do, but what I can say what a lot of them are going to do. And this is statistical mechanics, where we talk about how large numbers of particles behave rather than just one. Okay? Now, why did Erdman call this or name this the ice cream graph? Picture that you have two scoops of ice cream, and you put one down on a cold stone, and one down on a hot surface. The one on the cold stone will keep its shape longer and stay frozen, whereas the one on the hot surface will spread out and be more distributed as it melts. So at higher temperatures, you get more of a distribution of molecular velocities. Okay, and that's called a Boltzmann distribution. Now, I'm going to draw the same graph again. Don't laugh at my art skills, or lack thereof. But this time, instead of talking about temperature, Let's talk about molar mass. Heavier molecules will, on average, move slower than the lighter molecules. Okay? I think we understand that. I think that one actually makes sense to us. Okay? And what that allows us to introduce is the concept of root mean square velocity. What determines how fast a molecule moves? There's two factors. Temperature. We've already been talking about that. But also, in addition to that, it's molar mass. Okay? So, this is the Greek letter mu and the letters RMS. Velocity, root mean square, is equal to 3 RT over m, take the square root. So those average velocities that we're talking about will be equal to this. And what this tells us is that the velocity is directly proportional to temperature and inversely proportional to molar mass. Temperature goes up, they move faster. Molar mass goes up, they move slower. And I don't think I've actually really ever assigned a question where you have to calculate one of these. It's more a discuss it. Okay? Now, interesting implication of these ideas here is diffusion and effusion. Now, diffusion is a mixing of gases. If you exhale right now, what is coming out of you is mixing with other gases that are all around you. Okay? But effusion is the passage of a gas through a tiny hole into a vacuum. So if you were out in outer space, okay, and there was a small pinprick in your spacesuit, that gas would be effusing. Now, funky thing. Whether it's diffusion or effusion, it will still basically follow the same principles, because the distance between gas particles is on average so large that they're not really interacting very much. Okay? In fact, the distance that they have to travel before they hit another particle is often referred to as the mean free path. Okay? Now, this is illustrated beautifully by the NH3HCl experiment. Okay? This is one we would have set up in class for sure. You can find it on YouTube. We take a nice glass tube and we're going to put cotton balls in either end. Now, this cotton ball will have been soaked with concentrated hydrochloric acid, and this one with concentrated ammonia. Now, they will vaporize. The HCl and the NH3 will meet. These are both gases. And they will form NH4Cl solid, which is an ionic solid. That's white. It's a powder. Very easy to see. Okay? Except the interesting thing is it happens right about here. Okay? It does not happen dead center in this tube. Okay? It happens much closer to the HCl end than to the ammonia end, because HCl is heavier. Molar mass is about 36.46 grams per mole, and for ammonia it's about 17.04 grams per mole. Okay? calculating these velocities and comparing them came mathematically from a guy named Thomas Graham. Let's assume we have two gases that are at the same temperature, and if they're in the same container, they're at the same temperature. Okay? The kinetic energy of those gas particles equals 1/2 mv squared, where m is mass and v is velocity. So, if I have two gases at the same temperature, the kinetic energy of gas A will equal the kinetic energy of gas B, which means 1/2 the mass of gas A, it's its molar mass, times the velocity of A squared will equal 1/2 the mass of gas B times the velocity of gas B squared. Okay? Now I can do a little bit of algebra to that and see that the mass of gas A divided by molar mass gas B equals velocity of gas B squared over velocity of gas A squared. So I can compare the rates at which gases diffuse and use that to determine the molar mass of a gas. Okay, we'll come back on page 14 and do some of that mathematically. All right, Morgan, signing off.